edXL Further Pure, Complex Numbers 1, an Introduction to Complex Numbers. In this fourth session we'll be looking at dividing complex numbers. Just as a reminder, we're going to look at this multiplication. So expanding the brackets, 5 times 5 minus 2i times 5, 5 times 2i, and minus 2i times 2i is minus 4i squared. So that's 25 minus 10i plus 10i, and I squared is minus 1, so that's plus 4. And the important thing here is that these two terms have cancelled out to leave 29, so we end up with a real answer to the multiplication. So you may recognise this as a difference of two squares, and you'll have seen it in factorising, and we've used it when we rationalise surds. The method requires a sign change in one of the brackets, and it will always give a real answer when used with complex numbers. So we have a small investigation to look at. We've got 4 expressions there, and we've got to work out which of the following is not the same as the others. So one of the answers is 2 minus 3i, so we need to check which ones are the same as 2 minus 3i, or is that the odd one out. On first inspection it's not obvious which is the odd one out. They all appear very different. However, if we complete the first 3 divisions, we will be able to make an easy comparison with the fourth one. So just looking at this first division, if we want to simplify this, don't forget that I is the square root of minus 1 and is the surd. Therefore we can rationalise in the same way that you would have done with surds. So we can times top and bottom by I, so that gives us 3i plus 2i squared, and I squared is minus 1, and I squared in the denominator is minus 1. So if we divide the top by this minus 1 here, we get minus 2 divided by minus 1 is 2, and 3i divided by minus 1 is minus 3i. So I, just a reminder, is a surd when you are rationalising. So that one was 2 minus 3i. So we have a look at the next one, 13 over 2 plus 3i. So we need to take a little bit more care rationalising this one. So we look at the denominator with the 2 plus 3i, and we're going to times top and bottom by 2 minus 3i, the complex conjugate. Now carefully multiplying, we've got 13 times 2 is 26, 13 times minus 3i is minus 39i, and it's the denominator where the really helpful maths happens. We've got 2 2's are 4, we've got plus 6i, we've got minus 6i, and we've got minus 9i squared, and I squared is minus 1. And again we can see the plus 6i and the minus 6i cancelling out, so we get 26 minus 39i divided by 4 plus 9 is 13, so this one is 2 minus 3i as well. If we just check this last one to see what we get, we've got 13 over 2 minus 3i. We want to rationalise it, so we're going to multiply top and bottom by the conjugate of 2 minus 3i. And see what happens. We get 26 plus 13 times 3i, 39i, and the denominator is 2 2s are 4, minus 6i, plus 6i, minus 9i squared, and I squared is minus 1. So that's 26 plus 39i, and again we can see the minus 6i and the plus 6i cancelling out over 13, so that's 2 plus 3i. So you can see that 2 plus 3i is indeed the odd one out. Here's an exam style question. We're given z is 2 minus I root 3, and they are asking us to use algebra to express z plus 7 over z minus 1 in the form a plus bi root 3, where a and b need to be integers. So we're given z, so we're going to use the given z. Start off, just check z plus 7 is going to be 9 minus root 3i, so I'm going to put the I at after the root 3, and just checking the denominator, we've got z minus 1 will be 1 minus root 3i, and therefore the problem z plus 7 over z minus 1 will be 9 minus root 3i divided by 1 minus root 3i. We need to rationalise this, so we're going to times top and bottom. We look at the denominator, which is 1 minus 3i, and we multiply top and bottom by its conjugate, 1 plus root 3i. Don't forget to do the same to the top. So in effect we're multiplying by 1. So carefully doing the multiplication, we get 9 times 1 minus root 3i times 1. We get 9 times root 3i, and minus root 3i times root 3i is minus 3 times I squared. Be careful with the denominator. There's 1 times 1, there's minus root 3i, there's plus root 3i, and there's minus 3 times I squared, which is minus 1. Again, we are expecting the imaginary parts to cancel out. So, simplifying the top, there's 9 plus the 3 at the end is 12 plus 8 root 3i, and in the denominator we've got 1 plus the 3 at the end is 4, and the top will divide by 4 to give 3 plus 2 root 3i. So it's in the form required, and a is 3 and b is 2. Here's another exam style question. The complex number z satisfies the given equation. We've got to find z in the form a plus bi, where a and b are real. So if we take this problem, we need to find z. In other words, we need to rearrange this equation for z. Before we rearrange it for z, I would just rearrange for z plus 3i to start with. So that's 10 minus 5i divided by 2 plus i. We're now in a position to rationalise the right hand side in the usual way. We look at the denominator 2 plus I, and we're going to multiply the top and the bottom by its conjugate, pair 2 minus I. So doing the multiplication, we've got 20 minus 10i minus another 10i, and then there's plus 5i squared, so that's plus 5 times minus 1, and the denominator is 4 plus 2i minus 2i minus I squared, which is minus 1. Again, check that the imaginary part in the denominator cancels out. Tidying this up, simplifying it, we've got 20 minus the 5 at the end is 15 minus 20i divided by 4 plus 1 is 5. So now we have z plus 3i is 3 minus 4i, and now we're in a position to take the 3i away from both sides. So that's 3 minus 7i. In the next session we're going to look at terminology, including real and imaginary parts, and talking more about conjugate pairs.